All right, let's talk about a piece of tech that sounds like it's straight out of science fiction. It promises zero emissions, just like a battery EV, but with a 5-minute refuel time. So how on earth do you actually power a car with hydrogen, the most common element in the entire universe? Well, it's a fascinating story of some really clever chemistry and some seriously high-pressure physics.
I mean, think about that for a second. An electric car. Zero tailpipe emissions. But instead of plugging it in for hours, you just pull up to a pump, fill it up in 5 minutes, and you're good to go, just like a gas car. It almost sounds too good to be true, right? So how is that even possible?
Well, the answer lies in a totally different kind of electric car. It's called a fuel cell electric vehicle, or FCEV for short. See, instead of carrying around a massive, heavy battery, an FCEV has its very own power plant on board, one that creates electricity on the fly as you drive.
Now, this is the most important thing to understand. A fuel cell is not an engine. Nothing gets burned. There's no fire, no explosion. It's an electrochemical device. You can almost think of it like a battery that never runs out, as long as you keep feeding it fuel. It generates electricity just by reacting hydrogen with oxygen from the air.
So, how does this chemical engine actually pull it off? How does it make power? To figure that out, we have to shrink down and go right inside the heart of the system, the fuel cell itself.
Okay, once we're inside, we see 4 key players. You've got the anode, that's the negative side, and the cathode, the positive side. Right in the middle is the real hero of our story, something called a proton exchange membrane, or PEM. And sprinkled around, helping the whole reaction happen, is a platinum catalyst.
All right, let's watch this happen in real time. First, hydrogen gas comes in on one side, the anode. The platinum catalyst gets to work and splits each hydrogen molecule into positive protons and negative electrons. Now that membrane in the middle, the PEM, acts like the world's strictest nightclub bouncer. It looks at the protons and says, yep, you can come through. But it blocks the electrons, telling them, nope, not on my list. You got to take the long way around. So the electrons are forced to travel through an external circuit. And what is a flow of electrons? That's electricity. And that's what powers the car's motor. Finally, on the other side, at the cathode, the protons that pass through the membrane meet back up with those electrons, and they all combine with oxygen from the air. And what do you get? Water.
And that's the whole beautiful process right there. The only thing that comes out of the tailpipe is pure H2O. No CO2, no nasty emissions, just water. It's this incredibly clean, direct conversion of chemical energy into electricity. But, nothing's perfect. A modern fuel cell is about 55 to 60% efficient at turning the hydrogen's energy into electricity that actually moves the car. The other 45% or so, well, that gets lost as waste heat. It's actually why these cars still need a radiator and a cooling system, just like a regular combustion engine car.
So, creating the power is one thing. That's half the battle. But you also have to store the fuel. And trying to safely contain a highly pressurized gas in a car that's bouncing down the road, that is a massive engineering challenge.
Let this number sink in for a second. 700 bar. That is a crushing amount of pressure. To put it in perspective, it's about 700 times the normal air pressure around you right now. We're talking over 10,000 psi. Trying to contain that kind of force safely in a vehicle is, well, it's a monumental task.
The solution they came up with is a work of art called a Type 4 composite tank. On the inside, there's a simple plastic liner, but the real magic, the real strength comes from wrapping that liner in an incredibly thick layer of carbon fiber. A great way to picture it is to imagine wrapping a balloon in miles and miles of super strong thread to stop it from bursting. That's pretty much what's going on here, just on a much, much stronger scale.
So why are these tanks always shaped like long cylinders? Why not a sphere or a cube? Well, it comes down to physics. The pressure inside the tank is pushing out in all directions, but it creates 2 main forces, or stresses. One force tries to pull the tank apart lengthwise. That's called longitudinal stress. But there's another force, called hoop stress, that tries to split the tank open around its middle, kind of like a sausage bursting its casing. And here's the kicker. That hoop stress is twice as strong as the longitudinal stress. A cylinder is just the most efficient shape for managing that incredibly powerful force.
And the engineering that goes into this is just staggering. The force trying to split that tank open is enormous, but the carbon fiber they use is many, many times stronger than it needs to be. The key takeaway here is that every single tank is built with a safety factor of about 2.25. That means it is literally designed to withstand more than double its normal operating pressure. These things are built to be incredibly safe.
Okay, the tech is absolutely brilliant. There's no arguing that. But how does it really stack up in the real world? To answer that, we have to zoom out and look at the entire energy journey, from the moment the fuel is created to the moment it actually turns the wheels. This is what's known as well-to-wheel efficiency.
And here's where we hit our first big snag. Just the act of compressing hydrogen gas up to 700 bar is incredibly energy intensive. It uses up between 10 to 15% of the total energy that's in the hydrogen to begin with. That's a huge energy penalty you pay before the car's even moved a single inch. So when you add up every single step, making the hydrogen in the first place, compressing it, trucking it to a station, and then putting it in the car to convert it back to electricity, the total well-to-wheel efficiency is only about 25 to 35%. Now compare that to a battery EV. For a BEV, the path from the power plant through the grid to the battery and to the wheels is way more direct. You end up with a total efficiency of around 75 to 85%. Let's put that in even simpler terms. Imagine you have 100 units of clean energy from a wind turbine. If you use that energy to charge a battery EV, about 80 of those units will actually be used to move the car down the road. But if you use that same 100 units of energy to create and compress hydrogen for an FCEV, by the time it gets to the wheels, you're only left with about 30 of those original units. That's a fundamental challenge that's just rooted in the laws of thermodynamics.
But the engineering story doesn't just stop there. Researchers and engineers love a good challenge, and they are working on some pretty wild ideas to solve these problems, especially when it comes to the tricky business of storing hydrogen.
The roadmap for the future involves some really advanced science. They're looking at things like cryocompressed hydrogen, which is making it super cold to pack it in tighter. There's also liquid hydrogen, though that has its own issues with evaporation. But the real holy grail, the thing everyone is dreaming of, might be solid-state storage, using special metal alloys that can basically absorb hydrogen gas like a sponge and then release it when you need it.
And all of this leaves us with a huge final question. The technology in a hydrogen car is an absolute marvel of engineering, there's no doubt about it. But at the same time, it's fighting against some fundamental laws of physics when it comes to efficiency. So is this the ultimate engineering puzzle to be solved, or is it an energy dead end for passenger cars? It's really a fascinating debate between what is physically possible and what is practically efficient. And that's definitely something to think about.